Next on the panel, we're going to have Shinji Sumimoto. We selected him to be on the panel because of the enormous amount of work that he's done with Fujitsu on the K computer and the FEFS file system.
Okay. Hello again. And this talk about FEFS performance evaluation on K computer and Fujitsu roadmap towards Lustre 2.x. So I'd like to show how K computer achieves on the file system. So here's the outline of my talk. Riken and Fujitsu jointly developed a K computer, and now in the public operation, and still continuous system software tuning for more suitable. So I'd like to talk about in this presentation. Firstly, I briefly confirmation about the K computer and the FEFS overview, and then this is the main focus on the performance evaluation of the full system of the K computer. And next, I talk about the issue toward X scale. This is what we learned around the evaluation of the constructing the K computer. And finally, I talked about some brief overview in the roadmap. So here's a slide. Maybe you can see the last year. And here's a system overview of K computer. And K computer knows very well about two components. First one is a Spark-based processor and a Spark 64 8FX. So this is an 8-core processor using 128 gigaflops and 58 watts. And second component is the interconnect controller ICC. This is a six-dimensional torus mesh topology in a TOFU interconnect. This will provide a 140 gigabyte per second on a single node. And system boards include such kind of CPU and ICC with 8 DIMMs. And this is a system board for computing nodes. And this is using water cooling processors, ICC, and some power devices. So we took the low temperature water cooling because increasing component lifetime and also reduction in electric current. And here's the rack. And this is in 24 system boards and 6 IO nodes. So this composes 102 nodes in a single rack. And total rack system with 10 petaflops, it consists of about 864 racks. And in the designing of the K computer, our goal is that challenging realize the world's top 1 performance system and keeping a stable system operation over 80,000 node system. So here's a system configuration. Today's talk is focusing on the storage, so I'll talk about the storage component. And here's a computing node, such kind of pictures. And there's an IO node, just same node in the rack. And here's a local disk and local file system. This is connected by a 5-channel IO node directory. And here's a global disk. Also, this is a file server is provide IA architecture. So in a morning session talk, there's a need to big endian to read conversion. So we tested a K computer that's such kind of a functionality. So here's IO architecture of K computer. I talked about in the morning session. There are 2 types of storage. A local storage for job execution in the fast storage. So we use eternal this physical storage, but configuration is different, and 2.5 inch based and RAID 5. And global file storage is for shared use. So this is for shared use, so the same eternal storage, but the configuration is different. 3.5 inch based and RAID 6 based. And configuration of each file system is optimized for each. It's for a local file system. There are over 2,400 of OSSs. This is for high parallel. And for a global file system, this is very small, over 80 8 servers for big capacity. And I'd like to talk about some FEFS requirement of K computer. This is for features. First one is it's extremely large. Extra large volume, 100 petabyte and 1 exabyte. And second one is the maximum number of clients. It's in 100K to 1 million, and servers in 1 kilowatt to 10K is we designed. Second is, of course, it's high performance, and throughput the single stream and parallel. Maybe we are focusing on maybe a single stream I/O, gigabyte per second, and parallel around the terabyte per second class. And also, we had to reducing file open latency around the 10K operation per, at the full scale. So I'll talk about later, but to realize the high performance, the locality of the interconnect and the storage is very important. So we take the avoidance of I/O interference among jobs. This is our design policy. And servers are also important for such a scale in high reliability and high availability. So K computer is currently operating and continues 24 hours and 365 days. So it always continues to provide service against component failures. And fourth one is also very important, low resource usage. Because the K computer is used for application, for large-scale application. So application user needs more memory. So system software, including NPI runtime and file cache and OSs, limit its memory usage within 10% of physical memory. So because the K computer has a 16 gigabyte of memory per node, so system memory, including cache and whole thing, is within 1.6 gigabytes. But it is very difficult to implement, so I talk about the detail. So let's talk about the design issues for ultra-large scale file system. First is I'm keeping user available memory over 90% of physical memory. However, a client requires the order of number of servers memory statically. That's one of the issues. Second is maybe I already talked in the morning session, minimize the impact of OS jitter application performance. I'm talking about. So especially LLPing among all clients and OSs are terrible. So third one is the parallel performance. K computer has thousands of OSs and 5,000 and 10,000 of OSTs. So leverage I/O and communication performance among servers and networks also which is very terrible. Fourth one is also important to recovery performance. So let's talk about keeping users aware of memory over 90% of physical memory. We took 3 strategies. One is limiting file buffer cache for dirty buffers. Basically, Linux allocates a bunch of memory file cache. But in that case, we have some application failure in a very critical path. So it must be limited file cache for dirty buffers. Second is also maybe minimizing local buffer usage. This is also important for file system and MPIs, such kind of things. Third one is takes minimize the number of OSTs. However, this strategy affects some file I/O performance. So this is a very, very critical trade-off exists. So issue is the same, and maybe using 10% physical memory, and most important thing is basic memory allocation policy of Lustre is pre-allocation for max size system. This is very critical system which changes memory consumption. So, for example, we take 3 of example. So, I took this slide on SC. However, I took briefly. The issue is relocation buffer on the client is pre-allocated number of OST in Lustre. For example, buffer size, 8 kilobyte and maybe 10 and number of OST requests. In that case, when we use 1,000 OSTs, 80 megabyte per request required. For example, maybe 10,000, 800 megabytes per request. So because we limited the number, whole bunch of memory within 1.6 gigabyte, it is half amount of the memory. It's very terrible. So next one is the same one. This is when we create a file. Client allocates 24 bytes, but max number of OS index, the size of request buffer. It's also for request maybe 10,000 OS index. It is 234 kilobytes per request. So we took approach to reduce not max number of OST index, but we use existing number of OSTs. And also step in the number of striped OSTs, which must be reduced. And next one is request size OST data sent in close. This is when a client close the file, OST data, including all of OST information, is transferred from MDS to the client. This is increasing in population of number of OSTs. And if only maybe 10,000 OSTs, it may 312 kilobytes per cross needed, and also send in the from MDS to the client. This is also memory consumption and also make a performance degradation. So our approach is only send stripe number of OST and index of all OSTs. That is our solution. So let's talk about improving application performance for minimizing OS jitter. This is a problem. I can talk details, so I don't skip. But we solution is stopping broadcasting and clients. And secondly, the LDM problem. This is also presented by Oleg. Today morning session I skipped. So next slide I'll show how such OS jitter comes from the real machine. Here maybe a ping is a problem. I will skip this one. And here's the result. Here's the result in a real K computer using LL ping impact on MPI performance on the 1 peta processor, only 1/10 of the system. And here's this figure result is MPI barrier. Because K computer has a hardware barrier, it takes about 10 microseconds and for each MPI barrier. And here is a red plot is each time affected. Here is timeline, and this is 100,000 times. So, and ideally, it takes about 10 seconds. However, there's a much of OS jitter coming from, because for ideal case here is the baseline of MPI barrier. However, it is affected to up to 400 microseconds, 800 microseconds. Average is like here, so it affects 450 microseconds class of OS noise. It is 40 and 50 times worse. And so time is around twice as long and benchmarks. So here's a benchmark also in MPI altogether. This is fine number of message size. Here's a number of time. So we tried 5 tries. And ideally, a single line is really ideal. However, OS jitter affects the performance, and sometimes worse, and sometimes looks into it is not so stable. That's the problem. Usually, we have 2 times worse at 5 executions. So when we stop LPing, here's the next slide. Here, it's very, very clear. This is 10 microseconds, and maybe this y-axis is different. This is MPI barrier affects max maybe 250 microseconds class of OS noise. However, this is very clean, and here's some under the figures, and it takes over around 11 seconds. It's almost ideal. And also, the MPI altogether also the same in the 5 times twice or more ideal action. So that is very important for high-performance computing to limit such kind of OS jitter. So it's very important. So next is I talked about I/O zoning. This is also presented by the LUG 2010. The issue is job I/O conflicts on hardware. So sharing this volume and network links among jobs cause I/O performance degradation because of their connection. So our approach is separate hardware and among jobs. So here is a normalization. Job A and job B share the disk volume and interconnect. And this is also problem. So we take the allocation of the job to the local I/O node. So I'd like to talk about FEFS performance evaluation K computer. The evaluation environment in full system K computer, it provides 864 racks. And target is mainly focused in the local file system. I talk about a brief result on the global file system. And OSS is the I/O node. It's a memory of 16 gigabytes, and the number of OSS is 2,592 nodes. However, OSC we tell us maybe I talked on the RAID 5. However, to reduce memory consumption, we cut off half of the number of OSCs. So we measured several configurations on the RAID disk. So we took the RAID 5 plus 0. RAID 5 and striping technology, so it's the most small affects the storage performance. And this number of OSCs, so 5,184 OSCs. Currently, we designed them with 10,000 OSC, but we must reduce memory consumption. We took the half of the number of OSCs. And MSC is Intel Xeon, and the memory is 64 gigabytes. So we use a benchmark program in the IOR, the MT test. And in the IOR benchmarks, we measured with I/O zoning and without I/O zoning. And here is a local file system performance on 10 petaflops without I/O zoning. And IOR results using, I'm sorry, but we removed very slow OSSs, 17 OSSs we removed and measured. So it used 2,575 OSSs. And here is the result of the IOR using a project file per block and project shared file and MPI of shared file. And in the file block performance, write performance is almost 1 terabyte per second and 964 gigabytes per second. And the read performance, maybe last year I presented here an 80 petaflops system is 1.3 terabyte per second, but 10 petaflops also in the almost 1.5 terabyte per second. But the project file performance is okay. However, we have two issues. One is the project shared file slow read performance, and the MPI shared file, MPI file share, both of the read and write performance is very regulations. That's the problem. So after this is a full slide, I investigate why this performance is worse. Firstly, we measured IR performance statistics analysis by collector and read and write and read. And here, the upside is the IO write performance, and both on the file per block and shared and MPI shared. And here is the eruption time of the second, and here is the gigabytes per second. In the IO write case, statically continues to access 1.2 terabytes per second, and here is some time loss. So it is different from for each kind of benchmark. In the MPI case, it is started very, very fast and continues fast, but ending time is very long. And MPI 5 block is gradually goes up, and finally, top is, ending time is very fast. And MPI shares, starting time is very good, but end time is long. However, it is at 1.2 terabyte sustained performance, but there is no reason for slow MPIO. In a read case, it's very difficult to understand, but it is gradually in a file performance around 2 terabyte per second and keeping a long ending time. And POSIX shared and MPIO shared keeps around 1.75 terabyte on shared file. And shared file in the slow startup, slow ending. And MPIO in the fast startup but slow ending. This is a difference from. So it seems to be serialized by something. So next, we investigate the performance direction analysis, measure the elapsed time on client on open and read write and close. And here's the result. This is the right case. And in this figure, this is maybe a elapsed time per client. And in this figure, POSIX file per block and POSIX shared file is almost same, right? Almost same. However, MPIO shared file is much longer than open and also close time. So we invest in the problem and finally found this is maybe MPIO library setting. Because MPIO library uses a barrier on open and close file. So POSIX file per block and POSIX shared file system is running like this. However, MPIO shared file is open, barrier, and read write, and barrier. This is a time loss. So this is because we use 2 GB I/O per client, but it is too small to realize enough bandwidth. For example, for read write case, 1.2 terabyte per second. However, the benchmark result is around half. This is because open and close time, elapsed time, and the same time to the I/O bandwidth. So it must be increased number of file I/O to increase the bandwidth performance. These are also same. So next one is you evaluate the local file system performance with I/O zoning. This is because here's the result. And write case the same. However, read case is without I/O zoning, 0.85 gigabyte per second to up to the 1.4 terabyte per second. So read performance increasing by read performance will limit such kind of congestion network and congestion storage. And it's very and here's the result of statistics. Write performance is around 1.2 terabytes. This is the same. However, this performance is keeping over 3 terabytes per second and performance. But limit to the very, very small gigabyte per second. So half of benchmark is allocated. So when you use 8 gigabyte file for each client, it takes about 80%. So it is because write performance over around 1 terabyte per second, and read performance will be 2.4 terabyte per second by increasing higher. But we don't have a time to measure. So let me show a short global file system performance. This is very confusing. The same. We use Ethernet Layer 6 and 2800 of OSTs. And here's the result. And write performance is around 200 gigabytes, and read performance around 235 gigabytes per second. And this is because almost same as statistics and read and write. So here's the MT test performance. We measured performance by increasing number of clients. And here's a kilobyte operation per second. And we measured MKDL, create, RMDL, and link performance. And this value is evaluated by on 7 petaflop, and this is evaluated on 10 petaflops. And metadata performance degradation occurs by increasing number of clients. So we also investigated this performance. And here's the result. And here's the result. This means elapsed time, and here's the MT test. This is performance, and this is a disk write statistics and write and read. And here's the network. I'm sorry, the Japanese way. This is a receive and send, sorry. And this is CPU statistics. From the result, this is RMDL and MKDL and disk start RMDL. MKDL and RMDL using the metadata processing is stopped by journal data writing. And however, disk start is constantly good. Create is also stopped in the journal interface because disk write is here. So that's problem is journal writing for a so big scale system. So let's talk about issues towards exascale file system. FEFS already has exabyte level function. However, still a problem for extra large file system. Firstly, I like to talk about resource usage, especially memory. This is very limited number of clients. So firstly, client must mount 4 of number OSTs statically. In computer case, 5,000 of OST must be mounted. However, in MPIO case, a client only does a file into a single OST. So it needs to be dynamically mounted. That's a similar solution. And still needs to reduce memory consumption in the file system. And because number of OST was reduced to half for a local file system compared with design phase, because it takes much of memories. Second one is OST that I talk about. Everything does not fit to 1,000 OST system. However, in that exascale system, number of nodes is increasing, so we must reduce such kind of OST data. A third point is performance leveling among OSTs and network links. And this is very, very difficult to 1,000 of OSTs, so we must keep the levelize each OST keep in the performance. So finally, I talk about a brief roadmap. So I'm already started with Intel applying FEFS extension to the Lustre 2.x, and will plan to finish by mid of 2015. I talked, and here's a roadmap, and with in Fujitsu maybe a QoS function, directed quota, IB etc. Maybe we'll be back to the community. And summary and future work. So we describe performance evaluation of FEFS on the K computer developed by Riken and Fujitsu. And it takes over 1.4 terabytes per second. However, at the peak time, over 3 terabytes per second read performance, expecting startup at any time. But the problem is to limit such highly startup, highly down. So we still investigate the first problem on it. And in the future, we develop the newer version, Lustre 2.x, and continue to contribute to extension to Lustre community. Thank you for your interest.